So we're going to spend a little bit of time talking about the Earth's magnetic field. Now the Earth does have a magnetic field. It's almost like a giant bar magnet was just kind of stuck through the middle of the Earth, and then we can draw basically our field lines in based on that. So we do have a north and a south pole. Now in this diagram that I have here, this is just showing the magnetic field lines there. Now one thing that's important to note is that this north here is a geographic pole. And then this south pole here is also a geographic pole. And so that's why your field lines, they're coming away from south and into north. That's just because we're referring to geographics. This north geographic pole is the south magnetic pole. And so then we are still going into south and away from north. So just be careful with this diagram. This diagram is marked in the geographic poles for those ones there. So when we are looking at the poles, again, we have that north and south pole. So our north geographic pole is in the Canadian Arctic there. And then the magnetic pole, north magnetic pole is down in Antarctica. So watch for that flip there. Now the poles aren't actually in the same place. So a couple things with those poles. The geographic pole and the magnetic pole, they are relatively close together, but they are not perfectly aligned. Now don't memorize this angle. It does change from year to year as well. But they are somewhat offset. So the geographic poles are based on the spin axis of the Earth, and then the magnetic pole is then just where our compasses tend to point to there. So the other thing to keep in mind with the Earth's magnetic field, that it is constantly changing, and so it has been moving throughout time. So it tends to drift a little bit. Now we're not sure why it really drifts, but it does, and so you have to kind of make sure you're kind of keeping up with that one there. So if you are navigating, especially out in the other poles, all of your maps are going to have something called a declination angle on there. And that's basically the difference then between where your compass is pointing, because your compass points to the magnetic pole, and where you're, say, trying to get to, because your map is going to be all oriented then towards then of course, the geographic pole. So back, say, in the 1600s, the magnetic pole, and that's this one in blue, was kind of meandering throughout the Canadian Arctic here. So this is all Nunavut up here. And then around 1994, it kind of headed off into sea. So it's on its way to Russia right now. This is your geographic North Pole. It's just kind of in the ocean up there. But then this is your magnetic pole, so it's heading out. And so say if you are, say, down here, say somewhere, say you're on Baffin Island there, and you're trying to navigate your way basically towards the North Pole, what you have to realize is the direction you're trying to go is going to be towards here. However, if you're following your compass isn't pointing towards that. And let's say it's, just grab that there. So your year is, say we're close to 2020 here. So your compass is actually going to be pointing in this direction. And so that difference between where your compass is pointing and where your map is actually going to be, that's your declination angle overall. And so if you look at this angle, just kind of through here, that's going to be the offset. So what you'll do is you'll take your compass, it's pointing in that direction. Your map will have an angle, which tells you then basically how far over you need to get in order to get to, say, the geographic direction that you're looking for. So maps are updated constantly for this one, and that's going to be important because if you have, say, an old map, so say you're still coming from Baffin Island here, but your map was, say, 15 years or 16 years old back in 1994, I guess it'd be 25 years old, sorry. If you had, say, an old map there, now your line is going to be pointing back to there. And so if you look at the declination angle on that map, the declination angle is going to be much larger from here because there was a greater offset. So if you're actually along this one here, so if you're in 2020, your compass is pointing along here, but if you're using a declination angle from an old map, that's going to be much larger, so that's going to set you way off over here, and you'll be out towards Greenland rather than the North Pole there. But the difference between where your compass is pointing and the direction to your kind of true geographic north, that's your declination angle. And again, because that magnetic pole is moving, you need to keep those maps updated. Now, if you're navigating around the equator, the difference actually isn't that big because those distances are so big. But the further north or south, if you're down in Antarctica, that you go, the more important that sort of thing is going to be. Now, the other interesting thing about the Earth's magnetic field is that it seems to have flipped from year to year, or not from year to year, but over the thousands of years, actually. So it seems to be a little bit random how much it changes, but on average, it's going to be every 200,000 years. Now, that's not on schedule there. Again, it ranges from anywhere from 10,000 to 800,000 years, I think was the longest one. But on average, it's about every 200,000 years. So it's over a very, very large time scale. And we have no idea when the next one's going to happen or if it's going to happen again, but it certainly could. So where the evidence for this one comes from is if you go to what's called the Mid-Atlantic Fault region. So this is around Iceland there. They're volcanic islands, similar to how Hawaii was formed there. But you have basically a lot of active volcanoes there because you have the Earth's crust that's basically splitting apart here. So this would be kind of along that fault line. So you have a number of volcanoes along there where you get lava coming up from the center of the Earth there. So you have this magma that's very, very high in iron, which means it has a magnetic character. And when it's in the liquids form, it's very free to move around. And so when it's in the liquid form, it tends to align itself with the Earth's magnetic field. And then as it basically gets pushed back in this direction or the other direction, it hardens up, and then it remains kind of locked in that notation. And so what people have noticed then is if you kind of move away from there, you'll get a region here where all of the iron is kind of more or less pointed in one direction. Then you'll get another region where it's pointed in the opposite direction. And then in the same direction, opposite direction, and it basically just keeps jumping back and forth. And it does that at symmetrical distances on either side. Now the Earth's crust seems to move away, be kind of pushing away at a relatively constant rate, and so that's where our time is going to get there. So the speed on which the crust is being formed basically gives us then our time estimate there. Now again, that's assuming that it's been moving at a constant rate throughout the millennia, but again, probably hasn't changed that much, but at least gives us a rough idea of what the time scale is. And again, why it changes, we're not quite sure. The Earth's magnetic field is thought to be just because we have a molten iron core, and because that's moving around, that's probably generating that magnetic field. Moving charges can generate a magnetic field, but why it flips and why it drifts, we really just don't know why that is. The last thing we're going to look at then is something called a magnetic domain. Now, not every material has the ability to become magnetic. Something like aluminum is not going to form a magnet ever. But things like iron is the most common one. Also cobalt and nickel can as well. So these are referred to as ferromagnetic, which is basically ferro or ferrous is just the old term for iron. So magnetic like iron is what we're looking for here. You need to know that iron is magnetic. All of the other ones, cobalt, nickel, some ceramics, you don't need to know those ones are going to be possible magnets there, but make sure that you know that iron is. So what happens in a ferromagnetic material is we have these large groups of atoms, and these are very high numbers of atoms. Now it's still a very small amount because atoms are so small, but you get what's called a magnetic domain, where you get basically 10 to the 15, 10 to the 20 different atoms, and they kind of align themselves. So in this diagram here, each one of these arrows represents one magnetic field. And in, say, a bar magnetic, you're going to have any number of those ones there, so many, many of those ones. But again, whether they're aligned or not tells you whether the overall thing is going to have a measurable magnetic field. So if all of those domains are randomly aligned, the material then could be made magnetic, but at that point in time, it's not magnetic. If you magnetize that material, then what you're doing is you're aligning all those magnetic fields. Now, the better aligned those are, the stronger the magnet's going to be. If they're just mostly in the same direction, it'll still typically have a magnetic characteristic there. As long as kind of the net movement is all in the same direction, then you'll get basically a measurable magnetic field from those. Now, we do often refer to these as permanent magnets because you can create a magnet that stays basically magnetic. But even in a permanent magnet, it's still possible always to destroy the magnetic field. And so the easiest way to do that is just to heat them up. And so if you heat them up, what's going to happen then is those molecules start moving faster and faster, and you end up then with this randomized kind of domain there. So anytime you heat up a magnet, basically you're going to wreck those domains. And there is a maximum temperature over which then it can no longer be made magnetic. And so basically if you're below the temperature, it'll retain its magnetic characteristic. Once you hit that temperature, then all the fields or domains are randomized, and so it's no longer going to be magnetic. And any temperature above that, there's no way to actually align the fields. Now, if you're below the Curie temperature, it is possible to realign those. I just put them in a strong magnetic field. If you drop a magnet repeatedly too, again, you are going to start to kind of knock some of those fields around, and so that as well will also start to basically randomize those fields. They often recommend that you store magnets kind of stuck together because that's going to basically just kind of help realign their fields because it'll be then in the magnetic field of the other. So make sure you know that not all materials can be magnetic. Ones that can be are referred to as ferromagnetic. What's happening with those ones is you have magnetic domains, which can be either randomly aligned or perfectly aligned or well aligned. If they're randomly aligned, it could be made a magnet, but it just currently isn't magnetic. If they are aligned, then it is currently acting as a magnetic. If it's currently acting as a magnet, heating it up past its Curie temperature will randomize them, and so then can be the magnetism then of that can be destroyed. But if you place it in a strong magnetic field, then you can restore that magnetism there.